Have you ever really stopped to think about how your computer does what it does? I mean, right now you might have a web browser open, maybe some music playing, a game downloading in the background, dozens of things happening all at once. But your computer, it probably only has one main brain, one CPU. So how on earth does it juggle all of that without just freezing? It seems kind of impossible, right? Like one chef trying to cook a 5-course meal for 100 different people at the exact same time? Well, it turns out it's all a very clever magic trick. Today, we're going to pull back the curtain on that magic trick. We are diving deep into Chapter 6, CPU scheduling. This is the secret sauce, the core mechanism inside your operating system that creates that illusion of doing everything at once. So let's get into it. And to make sense of it all, we're going to stick with that kitchen idea. First, we'll talk about the basic problem of having just one chef. Then we'll figure out what makes a kitchen good in the first place. After that, we'll check out some classic cooking recipes, find smarter ways to line up the orders, expand our kitchen with more chefs, and finally, figure out how to choose the perfect menu. Okay, so let's set the scene. I want you to imagine your computer's CPU, the central processing unit, the brains of the operation, is a single, incredible master chef. And every single program you run, every app, every background process, that's a new order ticket that gets slapped onto the counter. The big fundamental challenge is this. With just one chef and a never-ending stream of orders, how do you possibly manage that chaos and keep everybody happy? Now here's a really fundamental idea you have to get. A program isn't just running full speed all the time. Its life is actually a cycle. It alternates. First you have what's called a CPU burst. That's our chef, hands flying, chopping, cooking, working hard. But then it's followed by an I/O burst. That's when the chef has to stop and wait for something, waiting for the oven to preheat, waiting for a file to load from the hard drive, or waiting for you to type something. The entire game of scheduling is to take advantage of that waiting time. Because if one order is just waiting around, our chef should be working on another one. An idle CPU and idle chef is a total waste.
So right away, we have to make a huge decision about the rules of our kitchen. Is it preemptive or non-preemptive? Non-preemptive is the simple one. Once the chef starts cooking a dish, they finish it. No interruptions, period. Even if the most important person in the world comes in and just wants a glass of water, they have to wait for that complex 3-hour-long banquet meal to be completely done first. You can see the problem, right? Preemptive is different. This is where the head chef can yell, "Stop that! This new order is more important, do it now," and the chef will switch tasks. This single choice dramatically changes how fair and, more importantly, how responsive our whole computer feels.
Okay, so before we can start comparing different ways to run the kitchen, we need to decide how we're going to keep score. How do we know if we're actually doing a good job? We need some objective measurements, some metrics for success. And there are really 5 big ones we care about. First, CPU utilization. Pretty simple. How busy is our chef? We want them cooking as close to 100% of the time as possible. Second, throughput. How many dishes are actually getting out the door every hour? More is better. Third, turnaround time. This is from the customer's point of view. The total time from the moment they place their order to the moment food is on their table. You want this low. Fourth, waiting time. This is a part of turnaround time, but it's specifically how long that order ticket was just sitting on the spike being ignored. And finally, maybe the most important one for us, is response time. This is how quickly the chef starts working on your order. It doesn't have to be done, but just seeing that they've begun makes you feel like the system is fast. For anything interactive, this is absolutely crucial.
All right, now that we know what we're aiming for, let's look at a few classic recipes, or algorithms, that schedulers can use to decide which order gets cooked next. We'll start with the really simple stuff.
The most obvious way to do things is just first come, first served. It's exactly what it sounds like. You get in line and you wait your turn. The orders are cooked in the exact sequence they arrived. It seems fair on the surface, but oh boy, it can be incredibly inefficient.
Let me show you why. Take a look at this example. 3 orders arrive one after another. Process 1 is this huge task that takes 24 milliseconds. It starts right away, so its wait time is 0. Great for P1. But look what happens to P2 and P3. They're tiny little tasks. They only need 3 milliseconds each. But since they got in line behind the big one, P2 has to wait the full 24 milliseconds just to start. And poor P3 has to wait for both of them, so it's waiting 27 milliseconds. The average wait time here is just terrible. This is called the convoy effect. A bunch of fast little cars getting stuck on a 1-lane road behind one giant slow-moving truck. So what's the logical solution to that convoy problem? Well, what if the chef could look at all the waiting tickets and just say,
hey, this one will only take a minute, let me just knock this out real quick. That's the whole idea behind shortest job first scheduling. You always pick the quickest task you can do next. The intuition is great. You clear out a bunch of easy orders, make a lot of customers happy really fast, and lower the overall average wait time for everybody.
And here's the amazing part. It's been mathematically proven that this strategy is optimal. You literally cannot get a better average waiting time than with shortest job first. So why don't we just use it all the time? Well, here's the fatal flaw, and it's a big one. It requires you to predict the future. How does the OS know how long a program's next CPU burst is going to be? It can't. It can guess, it can look at past behavior, but it can't know for sure, and that makes this theoretically perfect algorithm pretty much impossible to implement in the real world. This brings us to a much more practical, realistic solution, and it's the one that really powers the modern computers we use every day. It's called round robin. The philosophy here shifts from finishing jobs to providing good response time and fairness. Our chef isn't going to finish any one dish. Instead, they set a timer for a tiny slice of time. We call this a time quantum. Let's say 10 milliseconds. They work on order 1 for 10 milliseconds. Ding, the timer goes off. They immediately put it down and work on order 2 for 10 milliseconds. Ding, then order 3. Then they circle back around to order 1 again. Nobody gets their meal finished right away, but everybody sees that their meal is being worked on almost instantly. That response time metric goes way, way down.
But now we have a new problem. How long should that time slice be? This time quantum is a critical trade-off. If you make it too long, round robin just turns back into first come, first served. If you make it super short, the system feels incredibly responsive. But there's a hidden cost. Every single time the chef switches dishes, they have to put away the salt, wipe the counter, get out new ingredients. There's a cleanup process. In the OS, we call this a context switch, and it's pure overhead. No useful work gets done. If your time quantum is too small, your CPU will spend all its time switching between tasks instead of actually doing them. It's a delicate balancing act.
So far, we've kind of been treating every order as if it's equally important. But in reality, that's not true, is it? A quick click on a menu button should probably be treated differently than a long video export that's going to take an hour. It makes sense to organize these things.
And this leads us to a really clever, sophisticated system called multi-level feedback queues. Instead of one big line of tickets, imagine 3 lines, each with a different priority. The top queue is for VIP, urgent, interactive tasks. Our chef always checks this queue first. If, and only if, this queue is empty, do they look at the second queue for normal, everyday jobs. And only if that one is empty do they finally get to the low-priority queue for background stuff. But here's the feedback part that makes it so smart. If a process in that VIP queue starts taking too long, the system assumes it's not really interactive, and it gets demoted down to a lower priority queue. It's an adaptive system, and it's the basis for how many modern schedulers really work.
Okay, our one-chef kitchen is running pretty well now. But let's be real. Your phone, your laptop, they don't have just one CPU core anymore. They've got multiple. So what happens to our analogy when we expand the kitchen and hire more chefs to work in parallel?
Well, there are 2 main ways you can organize this multi-chef kitchen. The first is called asymmetric. This is where you have one master chef who doesn't cook at all. They're the boss. They just handle all the incoming orders and tell the other worker chefs what to do. It's simple, but that master chef can become a bottleneck. The far more common approach today is called symmetric multiprocessing, or SMP. In this model, every chef is an equal. There's just one big shared queue of orders, and whenever a chef finishes their task, they just walk over and grab the next one from the pile. It's a true team effort. But this team approach creates a new, interesting problem. Imagine Chef 1 starts making a complex cake. They've got the flour out, the eggs cracked, the sugar measured, all laid out on their personal workspace. That workspace is like a CPU's cache, super fast local memory with all the data it needs. Now, what happens if we suddenly move that cake over to Chef 2? Well, Chef 2 has to get all those ingredients out of the pantry all over again. It's really inefficient. This is why operating systems try to maintain what's called processor affinity. They try to keep a task running on the same CPU core it started on so it doesn't have to waste time reloading all that data into a new cache.
And this idea gets even more intense on huge server systems with an architecture called NUMA, that's non-uniform memory access. Think of our kitchen being the size of a warehouse now, with ingredient pantries on opposite ends of the room. For a chef working on the east side, it's way faster to grab ingredients from the east pantry than to run all the way across the building to the west pantry. A smart NUMA-aware scheduler knows this. It won't just try to keep a task on the same chef, it'll also try to make sure all the ingredients, all the data for that task, are stored in the pantry that's physically closest.
Phew,
We've seen a ton of different strategies, from simple lines to complex, multi-chef warehouse kitchens. So how in the world does an OS designer, a restaurant owner, actually pick one? How do they decide on the final menu?
Well, there are a few standard techniques. You can do some deterministic modeling, which is basically just doing the math on paper with a predefined set of orders. Or you can get fancier and run a simulation. You build a computer model of the kitchen and throw thousands of virtual days at it to see how it holds up. But at the end of the day, the only true test is implementation. You have to actually build the kitchen, open for business, and measure how it performs in the real world.
And that really brings us to the single most important lesson of this entire chapter. There is no one best algorithm. It just doesn't exist. It is always a compromise. The perfect scheduling algorithm for a scientific supercomputer is a terrible choice for your smartphone. And the algorithm in your smartphone would be a disaster in a real-time system like your car's brakes, where missing a deadline is not an option. The ideal scheduler is always a balancing act tailored specifically to what the system needs to do.
So, I'll leave you with this question to think about. If you were the lead engineer designing the next operating system for your own smartphone, what would you prioritize? Would you focus on pure efficiency, trying to minimize waiting time and get as many tasks done as quickly as possible? Or would you sacrifice a little bit of that efficiency to maximize responsiveness, to make sure the user interface always feels buttery smooth and instant no matter what? It's a trade-off. So, what's the right compromise for you?